In geometry, the terms point, line, and plane are described but not defined. Other concepts that are accepted intuitively but never defined include the straightness of a line, the flatness of a plane, the notion that a point on a line lies between two other points on the line, and the notion that a point lies in the interior or exterior of an angle. The following are descriptions of some of the undefined terms. A point, which is represented by a dot, has location but not size. That is, a point has no dimensions. An uppercase italic letter is used to name a point. Figure 1.8 shows points A, B, and C. Point may be abbreviated PT for convenience. The second undefined term is line. A line is an infinite set of points. Given any two points on a line, there is always a point that lies between them on that line. Lines have a quality of straightness that is not defined but assumed. Given several points on a line, these points form a straight path. Whereas a point has no dimensions, a line is one-dimensional. That is, the distance between any two points on a given line can be measured. Line AB, represented symbolically by AB with a line with double arrows on top, extends indefinitely far in opposite directions, as suggested by the arrows on the line. A line may also be represented by a single lowercase letter. Figures 1.9a and b show the lines AB and M. When a lowercase letter is used to name a line, the line symbol is omitted. That is, line AB and M can name the same line. Note the position of point X on line AB in figure 1.9c. When three points, such as A, X, and B, are on the same line, they are said to be collinear. In the order shown, which is symbolized A-X-B or B-X-A, point X is said to be between A and B. When no drawing is provided, the notation A-B-C means that these points are collinear, with B between A and C. When a drawing is provided, we assume that all points in the drawing that appear to be collinear are collinear, unless otherwise stated. Figure 1.9d shows that A, B, and C are collinear, with B between A and C. At this time, we informally introduce some terms that will be formally defined later. You have probably encountered the terms angle, triangle, and rectangle many times. An example of each is shown in figure 1.10. Using symbols and abbreviations, we refer to figures 1.10a, b, and c as angle ABC, triangle DEF, and rectangle WXYZ, respectively. Some caution must be used in naming figures. Although the angle in figure 1.10a can be called angle CBA, it is incorrect to describe the angle as angle ACB because that order implies a path from point A to point C to point B, a different angle. In angle ABC, the point B at which the sides meet is called the vertex of the angle. Because there is no confusion regarding the angle described, angle ABC is also known as angle B, using only the vertex, or as angle 1. The points D, E, and F, at which the sides of triangle DEF, also called triangle DFE, triangle EFD, etc., meet are called the vertices, plural of vertex, of the triangle. Similarly, W, X, Y, and Z are the vertices of the rectangle. A line segment is part of a line. It consists of two distinct points on the line and all points between them. See figure 1.11. Using symbols, we indicate the line segment by BC with a straight line over the top. Note that line segment BC is a set of points, but is not a number. We use BC, omitting the segment symbol, to indicate the length of this line segment. Thus, BC is a number. The sides of a triangle or rectangle are line segments. The vertices of a triangle or rectangle are named in an order that traces its line segment sides in order. Can the rectangle in figure 1.10c be named? A. X, Y, Z, W. B. W, Y, X, Z. Solution. A. Yes, because the points taken in this order trace the figure. B. No. For example, line segment WY is not a side of the rectangle. The instrument used to measure a line segment is a scaled straight edge such as a ruler, a yardstick, or a meter stick. Generally, we place the 0 point of the ruler at one end of the line segment and find the numerical length as the number at the other end. Line segment RS with a straight bar on top in symbols, in figure 1.12 measures 5 centimeters. Because we express the length of line segment RS by RS with no bar, we write RS equals 5 centimeters. Because manufactured measuring devices such as the ruler, yardstick, and meter stick may lack perfection or be misread, there is a margin of error each time one is used. In figure 1.12, for instance, RS may actually measure 5.02 centimeters, and that could be rounded from 5.023 centimeters, etc. Measurements are approximate, not perfect. In example 2, a ruler, not drawn to scale, is shown in figure 1.13. In the drawing, the distance between consecutive marks on the ruler corresponds to 1 inch. The measure of a line segment is known as linear measure. In rectangle ABCD of figure 1.13, the line segments AC and BD shown are the diagonals of the rectangle. How do the lengths of the diagonals compare? Solution. As intuition suggests, the lengths of the diagonals are the same. As shown, AC equals 10 inches and BD equals 10 inches. Note, in linear measure, 10 double quote means 10 inches and 10 single quote means 10 feet. In figure 1.14, point B lies between A and C on line segment AC. If AB equals BC, then B is the midpoint of line segment AC. When AB equals BC, the geometric figures line segment AB and line segment BC are said to be congruent. Numerical lengths may be equal, but the actual line segments, geometric figures, are congruent. The symbol for congruence is equals with a tilde on top. Thus, line segment AB is congruent to line segment BC if B is the midpoint of line segment AC. An angle's measure depends not on the lengths of its sides, but on the amount of opening between its sides. In figure 1.16, the arrows on the angle's sides suggest that the sides extend indefinitely. The instrument shown in figure 1.17 and used in the measurement of angles is a protractor. For example, you would express the measure of angle RST by writing M angle RST equals 50 degrees. This statement is read, the measure of angle RST is 50 degrees. Measuring the angles in figure 1.16 with a protractor, we find that the measure of angle B is 55 degrees, and the measure of angle 1 equals 90 degrees. If the degree symbol is missing, the measure is not always understood to be in degrees. Thus, you should always include the degree symbol. Measure of angle 1 equals 90. Bad. Degree symbol is missing. Measure of angle 1 equals 90 degrees. Good. Degree symbol is included. In practice, the protractor shown will measure an angle that is greater than 0 degrees, but less than or equal to 180 degrees. To measure an angle with a protractor, number 1, Place the notch of the protractor at the point where the sides of the angle meet, the vertex of the angle. See point S in figure 1.18. Number 2. Place the edge of the protractor along a side of the angle so that the scale reads 0. See point T in figure 1.18, where we use 0 on the outer scale. Number 3. Using the same outer scale, read the angle size by reading the degree measure that corresponds to the second side of the angle. See point R in figure 1.18. For figure 1.18, find the measure of angle RST. Solution. Using the protractor, we find that the measure of angle RST is 31 degrees. In symbols, measure of angle RST equals 31 degrees. Some protractors show a full 360 degrees and are used to measure an angle whose measure is greater than 180 degrees. This type of angle is known as a reflex angle. Like measurement with a ruler, measurement with a protractor will not be perfect. The lines on a sheet of paper in a notebook are parallel. Informally, parallel lines lie on the same page and won't cross over each other even if they are extended indefinitely. We say that lines L and M in figure 1.19a are parallel. Note here the use of a lowercase letter to name a line. We say that line segments are parallel if they are parts of parallel lines. If line RS is parallel to line MN, then line segment RS is parallel to line segment MN in figure 1.19b. For A, the set 1, 2, and 3, and B, the set 6, 8, and 10, there are no common elements. For this reason, we say that the intersection of A and B is the empty set. The symbol is an O with a slash through it. Just as A intersect B is the empty set, the parallel lines in figure 1.19a are characterized by L intersect M equals the empty set. In figure 1.20, the sides of angles ABC and DEF are parallel. Line segment AB to line segment DE and line segment BC to line segment EF. Use a protractor to decide whether these angles have equal measures. Solution. The angles have equal measures. Both measure 44 degrees. Two angles with equal measures are said to be congruent. In figure 1.20, we see that angle ABC is congruent to angle DEF. In figure 1.21, angle ABC is congruent to angle CBD. In figure 1.21, angle ABD has been separated into smaller angles ABC and CBD. If the two smaller angles are congruent, or have equal measure, then angle ABD has been bisected. In general, the word bisect means to separate into two parts of equal measure. Any angle having a 180 degree measure is called a straight angle, an angle whose sides are in opposite directions. See straight angle RST in figure 1.22a. When a straight angle is bisected, as shown in figure 1.22b, the two angles formed are right angles. Each measures 90 degrees. When two lines have a point in common, as in figure 1.23, they are said to intersect. When two lines intersect and form congruent adjacent angles, they are said to be perpendicular. Another tool used in geometry is the compass. This instrument, shown in figure 1.24, is used to construct circles and parts of circles known as arcs. The compass and circle are discussed in the following paragraphs. The ancient Greeks insisted that only two tools, a compass and a straight edge, be used for geometric constructions, which were idealized drawings assuming perfection in the use of these tools. The compass was used to create perfect circles and for marking off segments of equal length. The straight edge could be used to pass a straight line through two designated points. A circle is the set of all points in a plane that are at a given distance from a particular point, known as the center of the circle. The part of a circle between any two of its points is known as an arc. Any line segment joining the center to a point on the circle is a radius, plural, radii, of the circle. See Figure 1.25. Construction 1, which follows, is quite basic and depends only on using arcs of the same radius length to construct line segments of the same length. The arcs are created by using a compass. Construction 1. To construct a line segment congruent to a given segment. Given line segment AB in Figure 1.26a. Construct line segment CD on line M so that line segment CD is congruent to line segment AB, or the measure of CD is equal to the measure of AB. Construction. With your compass open to the length of line segment AB, place the stationary point of the compass at C and mark off a length equal to the length AB at point D, as shown in Figure 1.26b. Then the length CD will be equal to length AB. Construction 2. To construct the midpoint M of a given line segment AB. Given line segment AB in Figure 1.27a. Construct M on line segment AB so that length AM equals length MB. Construction. Figure 1.27a. Open your compass to a length greater than 1/2 of line segment AB. Figure 1.27b. Using A as the center of the arc, mark off an arc that extends both above and below segment AB. With B as the center and keeping the same length of radius, mark off an arc that extends above and below line segment AB so that 2 points, C and D, are determined where the arcs cross. Figure 1.27c. Now draw line segment CD. The point where segment CD crosses segment AB is the midpoint, M. In Figure 1.28, M is the midpoint of segment AB. A. Find length AM if length AB equals 15. B. Find length AB if length AM equals 4.3. C. Find length AB if length AM equals 2x plus 1. Solution. A. Length AM is 1/2 of length AB, so length AM equals 7.5. B. Length AB is twice length AM, so length AB equals 2 times 4.3, or length AB equals 8.6. C. Length AB is twice length AM, so length AB equals 2 times the quantity 2x plus 1, or length AB equals 4x plus 2.